This video is going to be on section 2.1, Introduction to Limits. This is the beginning of new material for the class. The main topics in this section will first look at pictures to understand what a limit means. This is very important as far as what we're going to be dealing with for the entire class. Everything is built on limits. Then we'll talk about some properties of limits, and finally evaluating limits of functions, meaning given a formula, how do we figure out this limit? So the first thing to do is talk about the graphical interpretation of a limit. So the study of calculus begins by looking at an idea called a limit. We begin by looking at the notation of a limit and see what that means on a graph. So if f of x is a function and x equals c is in the domain of f, right, so that just means you can plug in c being in the domain, then the limit, in quotes, the limit as x approaches c of f is written like this. So this is important notation. Definitely write down the what it means in words, and also in the symbol here we have lim for limit. Below it we have x arrow c. So x is the variable. So if our function's variable is like t or something, you would see t here. And we draw an arrow towards the number it's going towards, which is c. And we just have the function inside f of x. So all these parts are necessary. You can't just write limit, you can't just write the function, you can't just write the arrows or any combination, you have to write everything. So that's important notation. The first thing we'll do is I'll kind of draw a picture for you to explain what the limit means. But in words before we get there, what the limit is asking us is, what y value does the graph of f of x approach as x gets very close to the number c? And so c is just a number. It can be any x value you'd like. But for the purposes of explaining this, I'm going to keep it as c. Let's pretend c is right here as our x value. And then I'll draw a picture of just some random function. We don't need a formula for now, just to explain it. And what I'm going to do is point out the point on the graph at x equals c. And what I need to go along with this is the y value, which I'm just going to call, let's say, capital Y. Not important what this is called for now. Okay, but what the limit is asking us is, as we walk towards this point, what's the number here? So imagine you're walking towards x equals c on the graph. And you have to do it both ways, meaning we can walk towards x equals c from the left, we can walk towards x equals c from the right. And we want to answer the question, what y value are we walking towards? As we move towards x equals c on the graph from the left, as we move towards it from the right, kind of, you walk one way, you walk another way towards it, what y value are we going to? And the reason I gave this a name is the y value we are going to is just capital Y for this example. So what we would write is the limit as x approaches c of our function f of x equals capital Y. And if you don't like dealing with just the numbers, pretend that if c was 2 and y was 3, then we would have, as we walk towards x equals 2 from both ways, the y value we are going towards is 3. But we'll have plenty of examples with numbers in a minute. So that is the idea of a limit. As we walk towards it from both ways, what y value are we going towards? Now, one thing that's important that I mentioned is walking towards the x value both ways. It might be the case that you don't walk towards the same y value, which we'll have examples of in a second. And because of that, we need to actually talk about what's called a one-sided limit, meaning we only talk about what's happening as we go towards x equals c from the left and then from the right. So I'm going to go ahead and introduce one-sided limit notation. If we are asked to evaluate a limit from the left side, it will be written almost exactly the same as before, but with this minus error. It almost looks like an exponent, but it's just a minus sign on the c. Right, so just very quickly, if we have a little picture again, C, there we have our graph. Then as we walk towards it from the left, do that in red, or sorry, in orange to just match the color. The numbers, the x values are smaller over here, which is why we use the minus sign. Helpful way to remember. Right. So that would, if whatever y value we are walking towards from the left would just be a number that we would say that equals when we deal with the problem. And also same thing from the right, we have, instead of a minus, we have a plus. So plus sign means we're coming from the right. And the reason we use the plus sign is if we're to the right and walking towards C, the x values are bigger. It doesn't matter that y is bigger or smaller. We only care about the x values. And that's just a way for you to help remember when you use the plus or the minus. All right, so we'll go ahead and look at a problem to see how this works. Once again, we'll just be talking about a picture for now. It says for the graph of y equals f of x below, evaluate the following one-sided limits. So we have this picture, and I'll just scroll down for a second so you can see what we want to figure out. We will have the limit as x goes to 1 from the left, the limit as x goes to 1 from the right, and then same thing with 3. And then at the end here we have a little extra to talk about, just as a reminder of function notation. One thing I forgot to type in, which is something I'll edit in now, is you should have the function name in here. When you look at the homework, it'll be there. They should all have f of x in there because that's the function name. Alright, but this first one is asking what y value are we going to as x goes to 1 from the left. Minus sign is from the left. And then the second part that'll go along with it is the same thing. What y value are we going to as x goes to 1 from the right? And so what you want to do is, this will be on your computer, so you probably won't actually write on it, but just look at where x equals 1 is and just kind of make a mark here for yourself. This is where x equals 1. And as we go towards the left, what y value are we going towards? Well, this is the x-axis, that's where y is 0, so as we walk towards it, we are going towards y equals 0. That makes the answer to the first part 0. And then as we go towards 1 from the right, we want to get close to it. I know there's like a couple parts over here. You only care about being very close to 1, so we can just start by walking from 2 from the right and go towards 1, and that is also going towards y equals 0. And so parts A and B are both answers of 0. Right, now parts C and D are asking about 3. Now for 3, that is right here. This is where the graph breaks up. I'm going to go ahead and instead of drawing a circle, I'm going to just draw it in a dashed line so we can see. I want that to be black. Right, this is where x equals 3. The dashed line is just something I'm drawing and it's not actually there on the graph. Maybe not cover this part though. Right, and parts C and D are asking what happens, what y value do we go towards as x goes to 0, or x goes to 3 from the left and from the right. And if you jumped ahead, you might already be thinking that there's 2 different answers. If you are thinking that, you are correct. As we go towards 3 from the left, as we go, look on this line, what section are we on from the left? We're over here. So imagine walking, starting at 2, but we're going towards 3. The y value we are going towards, it doesn't matter that this is an open circle, because it's what y value we are going towards. So open circles don't matter for limits because it's just what we are going towards. And the y value we're walking towards is -1. So for part C, the answer is -1. The y value we are walking towards is -1 right here. And then as we go towards the 3 from the right, we want to look at this point, not this point down here, but this point up here, because towards the right, we're on this little section. So imagine walking from 4 towards 3 from the right. once again, open or closed circle doesn't matter. It's just what number you're walking towards. So I'll write the same thing as open circle, closed circle. Doesn't matter for limits. It only matters what you're walking towards. And what y value are we walking towards there? We're walking towards y equals 0. This point right here is where y equals 0. And that's the idea with one-sided limits. Sure, the picture might be able to look a little more complicated, but in this section, not so much. The next section, we'll see slightly more complicated things, and we'll talk about those. Now, for part E, f of 3 means what is the y value when x equals 3. This is not a new notation. And if you're looking at where x equals 3, we have two possible points. One has a closed circle, one has an open circle. This is when the closed circle, open circle matters, because the closed circle is where our function is. If it's the open circle, we're not including it. If it's the closed circle, we are including it. Because we're not walking towards it anymore, we're just looking right at it. And right here, this closed circle is at y equals 0. Right. We are not walking towards it. Don't walk. If they were both open circles, then it could be D and E. They can't be both be closed circles, because then it wouldn't be a function. It can only spit out one number. Right, but that's one thing to not get confused on. Something that's old. It's still the same. The limit thing is new. Old things still work the same. Right. Here I'm just outlining a few things about the problem above. One is that the one-sided limits can be the same or different at some point. So at x equals 1, the one-sided limits were the same. At x equals 3, they were different, and that's okay. Part C approaches what is called a hole. So an open circle on a graph is called a hole. The limit still exists here, even though the function value does not have the same number. Well, all we're saying here is that the limit here was different, -1 than 0. But that's because they're different ideas. Limits are what we're walking towards. Function values are where it's filled in. We're just looking at it. Part 3 is what we already touched on. It doesn't matter if we have an open or closed circle when we're talking about limits. And part E is a reminder that a function value is the y value on the graph that is filled at the specific x value. So just recapping everything we did up there. You may be not familiar with a hole. We'll talk more about those throughout the class, and even later in this section. All right, so there is one theorem. There are a lot of theorems in calculus. Basically, they provide formulas or ideas that are true, and you will use them. So our theorem here says let f be a function and c be a number. Then the limit of f of x as x approaches c exists if the limit as x approaches c from the left or equals the limit as x approaches c from the right. Right, so, and if so, the limit value, so notice how right here we don't have the plus or minus, it's just saying the limit value equals the same number as the one-sided limit. So just kind of to recap this theorem, if the one-sided limits are the same, then that is the limit value. And if the one-sided limits are different, the limit does not exist. So just kind of to go back to our previous problem, if we were talking about just the limit, not the one-sided limit, we would say the limit is 0 at x equals 1. Since they are the same, we would say the limit as x equals 3, at x equals 3, does not exist because the one-sided limits are different. Okay, but we'll practice this again. So this one says, consider the graph of y equals f of x below to answer the following questions. Let me scroll so I can have it all in here. We have our picture here. It looks kind of overwhelming. There's a lot of little things going on. One thing I want to point out is all these tick marks that they have here are intervals of 1. So that's -1, -2, 1 and 2. I'm not going to fill them all in, but they're all 1. And then let me fill out the f of x part here for the limit. Right, so even though this problem has a lot of parts, all of this should, reach all the possibilities of what we have to worry about as far as limits go for a picture. Alright, so the first 4 parts are dealing with x equals 0, and the last 4 parts are dealing with x equals -1. We'll deal with 0 first. And so x equals 0, that is the y-axis. That's what we'll point our attention to first. And the first part asks, what is the limit as x goes to 0 from the left of f of x? So we're walking towards this point from the left. Remember, just take the closest little segment. You don't have to walk from back here. And the y value we are going towards is 2. And we're going through this spot right here. Doesn't matter if it's open or closed. We're going towards this spot. Now if we walk towards x equals 0 from the right, we're going to the same y value. As you can see, we're going to 2 still. That point right there. So they're both 2. Well, what that means is the limit itself, since these are the same, for part C, the limit as x goes to 0 of f of x is also 2. Right, so anytime they approach the same number, the limit is that number. And that's our theorem from above. And the limits, the one-sided limits are the same, then that is the limit value. Now part D, just once again a reminder of function notation, f of 0. For f of 0, we look here and you'll notice that the only spot on the graph actually has an open circle. There's no closed circle anywhere where x equals 0, so this is D and E. F of 0 does not exist. And that's okay. You can have D and E for anything. You can have a number for anything. It just depends on the problem. Right, now the next spot we want to turn our attention to is x equals -1, which is right here. And do the same thing. All right, as we go towards -1 from the left, since we're looking at this spot right here, we notice from the left we should be on this side. What's the y value as we walk towards that? Well, it's -1, 2, 3, 4. The y value is -4. That was not a good choice of color. Let me do that. So we're going towards -4 as we go towards -1 from the left. And as we go towards -1 from the right, we would want to be on this little section here, walking towards it from the right. So it's kind of like looking at exactly where the red marks are, but the other way, because we're going towards -1. And the y value it's going towards, if you look up here, 1, 2, 3, 4. We're going towards y equals 4. And the thing you want to notice about these is these one-sided limits are different. And what that means is that the limit itself does not exist. And once again, that's what this theorem says. If the one-sided limits are different, then the limit does not exist. You'll catch on pretty quickly about when the limit itself exists and when it doesn't, because really if it's attached at the point we're talking about, like at 0 here, then it did exist. If it's not attached like this, so it's like two different segments here, then the limit itself does not exist. Right, but use the one-sided limits as long as you need to. After this section, we don't really use them much specifically, but you cannot forget that we have to go towards that number from both sides, the same number. Right, now the last thing, f of -1. We look here at -1. Do we have a filled in circle? And we do. It's down here at the -4. So f of -1 equals -4. Right, but as we saw in the previous parts, that could be D and E as well. You just have to look and see what's going on. Right. The next little section, properties of limits. So really what we ultimately want to do is be able to do limits if we have just a formula, but we don't want to have to graph the whole thing to do it. Right, so the way we do it is dealing with some properties. And there's a long list in your book. I actually don't like to really bring it up because ultimately what all the properties will tell you to do, and this is exactly what I'm going to do, it's going to tell you to plug in the value and see what happens, with the exception of piecewise functions. And the reason this is the exception is piecewise functions often look like graphs like these. They have a section, separate sections, and you don't know which sections might be attached and which might not. So we got to be careful when we deal with piecewise functions. Okay. All right, but with that, I'll break down, these first couple here, and I'll even show you with the graph on the first one, since the number will work out pretty well that it does work. So if we want to figure out the limit as x goes to -1 of 6x plus 1, the first thing to do is notice this is not piecewise, which means we want to just plug it in right away. And that's exactly what it sounds like. We take our 6x minus 1, we plug in -1. 6 times -1 is -6, plus 1 is -5. Now I'll go ahead and tell you that that will be the answer, but if you're since it's the first one we're dealing with, how do we know it's actually the answer? Well, let's go ahead and graph y equals 6x plus 1. You don't have to do this, but oops, I forgot the negative. Negative 6x plus 1. I'll hit zoom and 6 to make sure we're in the correct thing. Did I type it in wrong? 6x plus 1. Guess it's too early. So we have our graph of y equals 6x plus 1. And then if you want to figure out what the limit value is, what you can do is, oops, I guess I hit second by mistake. If you want to just trace, you can kind of see on the graph here when x is -1, if we kind of go down towards where the graph is, it's about right here. And if you look at the y value right there, we have -1, -2, -3, -4, -5. So it looks like it works. But if you want to just hit over a couple times, you can see the x value when it gets really close to -1. And you won't be able to get perfect unless if you zoom in. We're kind of close to -1 here, and the y value is kind of close to 5. If you want to zoom in, hit zoom to right around that point, and then you can see we can get much closer to 1. Oops. You got to make sure you hit trace though. And here x is kind of close to 1 and y is kind of close to -5. So it'll work out. The main thing about graphing these is when you do graph them, if you want to check your answer, if your answer is not right, you just want to see, is it the graph breaking or not? And this is a line, so it's not breaking at all. All right, but the next one, this is first one, this is a line, we could have graphed it ourselves. This next one isn't something you would want to try to graph and figure out the y value from. You just want to notice that it's not piecewise. So go ahead and just plug it in. And this time we're asked to plug in x equals -7. All right, so make sure you are careful with how you plug it in. We got -7 squared minus 5 over 7 minus -7. Okay, so -7 squared is 49 minus 5. And the double minus gives us a plus on the bottom. 7 plus 7 is 14. 49 minus 5 is 44. And you don't want to make decimals. You want to leave fractions, but simplify the fractions. Here we can take a 2 out of each. We got 22 over 7. Once again, since this is not piecewise, this is automatically going to work. We'll see below a couple issues that could pop up and how to fix them. But leave it as simplified fraction. But if you want to graph this, see, trace along the graph towards -7, see what the y value is. You can compare it to 22 over 7 and it will work out just fine. Right, so the above limits were able to be evaluated simply by plugging in because they are not piecewise functions. That's the main thing to know to plug it in at the beginning. And the other thing is that it spits out a number. Right, so we'll see in examples below, we might have a 0 on the bottom, and we know dividing by 0 is bad. So that's the point here. When I say spits out a number, it's not dividing by 0. If functions are defined piecewise, you must check the one-sided limits before determining whether a limit exists. And that's very much because you don't know, as far as what the graph looks like unless if you graph it yourself, whether it's attached or not at that point. All right, so that for this piecewise function here, we have f of x equals 13 minus x squared for x is less than or equal to 0, and 13 plus x squared for x is greater than 0. Right, so one thing that's very important about piecewise functions, we have one here. Really, we only care about where it's breaking apart. And the graph is breaking apart into its two spots at x equals 0. Why this is important is if we want the limit at any x value that is not 0, all you do is plug into the appropriate one. Right, so you've dealt with piecewise functions before. If we wanted to figure out the limit at -1, -1 is less than or equal to 0, so we'd plug it in this one. If we wanted to figure out the limit as x goes to 1, 1 is bigger than 0, so we plug it into the second one here. All right, so that's what I mean by the appropriate one. Now if we want the limit as x equals 0, which you can see by the question here, that's what we want, you're gonna want to plug it into both and then compare the one-sided limits. Because that's where it's breaking apart. All right, so the first one, just be careful here. This one asks for the limit as x goes to 0 from the right first. All right, so from the right, the x values are bigger than 1. Or bigger than 0. And if we're dealing with bigger than 0, that's where it's greater than, so we want to plug into the second one. Okay. So for the one-sided limit for the right, we plug into the second one, because that's where it's bigger. The x values are bigger than 0. And when we do that, we get 13 plus 0 squared equals 13. And that's the one-sided limit. It's just going to be a number, like we've been dealing with. Now the second one from the left means the x values are smaller. Right, they're negative. So when the x values are smaller, that's where the first one comes into play. Because negative numbers to the left, numbers smaller are less than. Right, so we got 13 minus 0 squared. Right, plugging it into the first one, and that equals 13. Now, regardless of whether these work out the same or different, whenever you see a piecewise function, this is your thought process. Do I need to plug it into both or just one? Look at where it breaks apart. If you have to plug it into just one, plug it into that one and you're done. If you have to plug it into both, do it like we did here, and then compare the answers. Since these are the same, the limit is 13. And since the one-side limits are the same, The answer is that number. If these were different, then we would say it does not exist. All right, so for number 2 here, what you will notice is that we have a piecewise function. We want to evaluate some limits, and we do not, you'll notice we're not even worried about the one-side limits. It's not that you don't have to worry about them. The problem's just giving you this question that really wants answered: what are the limits? So the first thing, like we mentioned before, is to see where it breaks apart, because that's where we have to worry about which one it is. And this one breaks apart as x equals 0 again. Okay, so any limit value besides 0, which is part B, we'll have to do both for part B. But for parts A and C, the limit is not focused at 0, so we only have to do the appropriate one. All right, so for part A, we want the limit as x goes to -4 of f of x. -4, well, that's less than 0. So we want to plug into the top. We got 4 times -4 over -4 plus 4. 4 times -4 is -16, and -4 plus 4 is 0. Okay. So here's something that's new. We got 0 on the bottom. And I'll go ahead and tell you right now, when you have 0 on the bottom and the number on top is not 0, that is D and E. So if you have 0 over 0, which we'll see an example of after this, you'll see that that can change. It might not be D and E. But if you have a number that's not 0 over 0, it's D and E. So this limit is D and E for that reason. If you want to jump ahead and do part C before you do part B, for doing both, let's go ahead and do that. For the limit as x goes to 4, 4 is bigger than 0, so we'd use the second one. Plug into the bottom. And we got 4 times 4 over 4 minus 4. And you see the same issue here. 4 times 4 is 16 over 4 minus 4, which is 0. And for the same reason, this is D and E. We have a number that's not 0 over 0. Right. Now for part B, we have to plug it into both. You'll notice from above, since we had to answer the one-side limits, we had to be careful which one we did first and second. But this one, you just plug in both and check if they're the same. So let's plug in x equals 0 for the top. We got 4 times 0 over 0 plus 4. 4 times 0 is 0. 0 plus 4 is 4. And 0 on top is fine as long as the 0 is not on the bottom. This is 0. Now for the bottom, we want to plug in 0 on the bottom. We got 4 times 0 over 0 minus 4. 4 times 0 is 0, and 0 minus 4 is -4. Once again, as long as the number on the bottom is not 0, and the top number is 0, then that's 0. All right, since they are the same, we have that the limit as x goes to 0 is 0. If they were different, then it would be D and E, just like we mentioned before. And like in parts A and C, or the ones we did before, if we plugged in and got just a number, that would be the answer. But we didn't get just a number on these, we got division by 0, which is bad. Now, we won't have a ton of piecewise functions in this class, but they will pop up every now and then, and you need to know, or you really need to remember piecewise functions. The main thing is I gotta split it apart. It gets split apart. I have to check if it's a bad part where it's being split. Otherwise, you can just plug in. So this kind of summarizes what we're talking about. We see in the previous example that it is possible for a limit to not exist in parts A and C, even though we did not have to do one-sided limits. This is because we are not allowed to have a limit of the form number over 0 as long as the number is not 0. Here's the one special thing that will have, and it will be true throughout this class when we do limits. If you have a limit that evaluates to 0 over 0, this is a special form called indeterminate form. And what that means is you can't determine what the limit is. It is impossible to tell whether a limit exists or not if you have 0 over 0, but we can figure it out. What you must do in this situation is factor and cancel out any common factors. This will get rid of the 0 over 0 issue. Alright, so just to summarize this, because it's so important. 0 over 0 for a limit means what you want to do is factor, cancel, and plug back in. Alright, because you're going to plug in at the start, you're not necessarily going to know if it's 0 over 0 just from looking at it. So if you do get 0 over 0, this is what you're going to do. And I'll just kind of, recap the other things because this can still happen. I'm not saying everything we do from now on is going to be 0 over 0. If you get a number over 0, the limit does not exist. If you get 0 over a number, that's just the 0. And if you get just the number, that's what the limit is. And so this is the one that's going to be the most weird, but you're probably going to see it the most, which means you'll get used to it. And this is really a good summary for this whole section. Alright, so we got one problem here, just to sort of illustrate all 3 points. Well, not all 3 points, but the main new point with some different points. It says, let f of x equals x squared minus 7x minus 18 over x minus 9. Alright, it's not piecewise. Which means we're going to plug in right away. And the first part we're going to plug in is plug in 9. Alright, so you don't know what's going to happen. You might be able to tell right away that the bottom's going to be 0, which is fine, but you don't know what's going to happen to the top. So you got to plug it in. Plug in 9, we get 9 squared minus 7 times 9 minus 18 over 9 minus 9 equals 81. 9 squared is 81 minus 7 times 9 is 63 minus 18 over 9 minus 9 is 0. And then if you do that out on the top, you get 0. So it's 0 over 0. And this is exactly our indeterminate form. All right, so what that means is we've got to factor the original, cancel. You will be able to factor these, you will be able to cancel them as long as you get this 0, 0 correct. and then plug back in. Alright, so let's go ahead and factor. X squared minus 7x minus 18 over x minus 9. Right, we can factor the top. You should get a matching factor. So there should be an x minus 9, and x plus 2 is the other factor. They multiply to negative 18, they add to negative 7, so it works out. And then we can cancel the x minus 9s, and that leaves us with just x plus 2. So now we can do the limit again. We don't have a fraction this time, so we know it won't be 0 over 0. And we plug in our x equals 9 here. Right, now to be formal about this, what you would do is say you want to do the limit as x goes to 9 of x plus 2. Then plug in the 9, so we get 9 plus 2, which is 11. And that'll be our answer. Now I'm going to show you the graph of this because there's something funny that happens on the graph at 9. It's actually going to be a hole whenever you have 0 or 0. Well, not every time, but most of the time you have a hole. And let's go ahead and graph the original. So we had x squared minus 7x minus 18 on top, divided by x minus 9. Now if we hit zoom 6, the original, we're not going to see where y equals 11 because it goes up to 10. Also, we're interested in what's happening at x equals 9, so if you hit window, since we only care about where x is 9, maybe let's do from positive 5 to 10. The 9's inside there. And then the y value we care about, we think y is around 11. So let's say from 5 to 15. So if we trace along here, we want to go towards x equals 9. And we're getting there. It looks like it's definitely pretty close, going to be close. And you can see it's really close, 9.01, the y value is really close to 11, so it probably works just fine. What I want to point out here, there's no hole in the graph, so you wouldn't think there would be a hole there. But if we try to calculate the value f of 9, so if you plug in x equals 9, it's going to tell you the y value when we plug in x equals 9, and you'll notice that there's nothing. That means there's a hole there because the y value does not exist. But there's still the limit. Right, so kind of just something to be aware of. You can graph them to see the picture, but you might be missing stuff. If you just graph this, you're missing the hole, and that hole might be important to our problem. Right, now the other two should be perfectly fine because the only number that makes the denominator 0 is 9. So really, these last two should be just plug it in and good to go. So you want to go ahead and plug into the original. It's not a good idea to plug into the factored thing or automatically factor it because you can't factor it unless if you're doing a limit. And we don't do limits for everything in this class. So only factor when this happens. We're going to plug in x equals 0 into the original. So we got 0 squared minus 7 times 0 minus 18 over 0 minus 9 And all the 0 parts go away. We have negative 18 on the top and negative 9 on the bottom. The negatives cancel out, and 18 over 9 is 2. And that's it for this part. We got our number out. That's the limit. And then the last part, negative 2. Plug negative 2 into the original. And simplify this out. On the bottom, that's easier to do. That's negative 11, negative 2 minus 9. On the top, negative 2 squared is 4. Negative 7 times negative 2 is positive 14 minus 18. And 4 plus 14 is 18, so 18 minus 18 is 0. 0 over negative 11 is 0. And that's fine, our limit can be 0 all at once. Right, and as far as limits, this last one is more along the lines of what we'll see. A function, if we want to deal with a limit, plug it in. If it's 0 over 0, we need to factor and cancel. If it's not 0 over 0, just kind of look at what it is. So the important thing with limits is if you see a piecewise function, you must know to go through and do the steps to check. Right, but the last two problems we did really summarize the whole section. We're not going to do a ton with pictures throughout the entire class. It's mainly going to be formulas. The pictures just help us understand what a limit is.